There's a trail.
All right.
Definitely use. Yeah.
All righty. Happy Friday, you guys. It's almost weekend, huh? What's that, Emma?
Just you standing between me and the weekend.
I'm leaving. Okay. It's like me when I'm at a conference and they give me the presentation just before lunch. Ah, standing between the audience and the lunch. Yep. Okay, let's do some recap and we'll hopefully finish this section, the data, and get into sample preparation. It's the most exciting chapter of the entire book. No, but we'll get through it. Okay, so what's the difference between accuracy and precision? Do you wanna, anybody smiling at me?
Sure.
Or Golden is hiding from me?
I guess accuracy is how close you are to the true value.
Yeah.
And precision is like how close they are to each other.
The applications.
Yeah.
Okay. Very good. And then in what case can you give an example where coefficient of variation is a better measure of precision than standard deviation? We kind of gave an example last time. Do you remember the equation of coefficient of variation? How do you determine it? Over the mean. Yes. So coefficient of variation takes into account your measurement, the size of your measurement. So if you have multiple samples that might have different moisture content or protein content or fat content, and you're trying to compare a couple of methods to each other over a couple of different samples, you really have to correct for the size of the mean in order to determine the precision. You'll see that as important because some methods are better suited for a particular type of food than other methods. So when you work in the lab in a couple of weeks and we're evaluating different types of food, you'll notice that method X is better for cereals, method B is better for dairy products, for specific composition analysis. So that's why it's important to compare across different samples and different methods. And in this case, coefficient of variation is important. What do we have? That's you, Allie? Okay. You're reminding me that I'm standing between you and the weekend.
No, I didn't know my volume was on.
It's okay. I do this all the time. It's fine. Unless you're playing a game. Uh-huh. What game was it?
Oregon Trail.
All right.
Locked in now, I'm sorry.
You're fine. You're fine. We all need a little bit of a distraction once in a while. Okay. This next question, we haven't gotten to it yet, but I think we're going to come to it. Let me see where it is. Yeah, a couple of slides down. So I'll skip it for now. Everything else in gray, we haven't covered yet. But this recap question slide, you can use it when you're studying. You can go back and you'll find the answers when you study. All right, so we briefly talked about different sources of errors and types of errors. And we have three main categories for these kind of errors. There are errors associated with something beyond your control. It's not, you're doing the experiment, you're doing everything right, but something is really messing you up. Either let's say the spectrophotometer that you're working on, the bulb is dying. So all your absorbances are really low because the intensity of the light is low. That is something has to do with the instrument. You really have to change the bulb on that spectrophotometer. Another error that is very common is balance is off, analytical balance is off. It needs calibration. Or a mechanical pipette, that happens more often than not, that you're working with a mechanical pipette and then it deviates from what it's supposed to be dispensing. So all of your assumptions, you are pipetting 1 ml, constantly pipetting 1 ml, but in reality, you're pipetting 0.8 ml because the pipette is not calibrated. This kind of systemic error is mostly will offset your accuracy. Most of the time, it's your accuracy, not your precision. Random error has to do most of the time with you. I give you a different example here, but most of the time you're the experimenter, you are in the lab, you might have some variation due to how you're pipetting, not exactly the same every time. So when you do statistical analysis and you run an ANOVA, analysis of variance, in the ANOVA table, if you've ever seen an ANOVA table, there is the error factor, the experimental error factor. So if you have that experimental error factor small, you will be able to see significant difference among your treatments. If it's really large, you won't see any impact of your treatment. So random error is something that you can minimize if you're an experienced researcher. Or even if you're an experienced researcher, if it's a new method, you have to practice it multiple times to get good at the different components of that assay. Now, the other example I have here, and I point out a lot during the lab, is sometimes you want to weigh a sample. Let's say you're doing ash analysis, total mineral content, ash analysis. So you have to put your sample in a container we call crucible. So you put your sample, you have to weigh it, you have to record the weight. The next day, when we take it out of the furnace that ashes the sample for you, you have to weigh it again to get the mass of the ash. If you go to weigh it on a different analytical balance, that's going to cause error. So we usually tell you, write down the type of the number of the balance that you used for your samples. When you come back, you have to use that particular balance. This can impact accuracy and also precision. Let's say you're working in a group. You tell your partner in the group, go weigh half of these samples on this balance, and I'm going to weigh the rest on that balance. What are you doing? You're creating two different types of error associated with two different balances. So even if you're working in group, don't use two different balances, for example. Okay. Blunders. Oh boy, we always have blunders. We have many examples of blunders, but one common one is you use the wrong reagent. So done a lot in the past with students in the class, with graduate students, with me personally. So it does happen to anybody. So let's say you are determining, let's say you're titrating and you need to titrate using NaOH. We use that a lot for, oh, no, you want to titrate with HCl. We do that, for example, in the protein analysis lab, CalDAL, we titrate with HCl as the last step. And instead of putting 0.1 normal HCl in the burette, we put 0.1 normal NaOH. What's going to happen? We're going to titrate, and no change in color. So that we call a blunder. You lose your sample, you have to start over the analysis. Good thing you are the Wednesday lab Usually blunders happen in Monday lab. Just like Monday morning, coming out of the weekend, and things can go wrong. These kind of blunders, so in these kind of errors, so in your lab report for the next week, there's one question that asks you what type of errors you encountered in the lab. So you want to think, did you encounter systemic error, random error, blunders, and then you would answer the question accordingly. All right. So now we want to learn the difference between sensitivity and detection limit. Detection limit, sometimes you hear the word threshold. So what's the threshold of the detection of your unit? Do you know what we mean? Sensitivity is a little trickier, but do you know what we mean when we say detection limit or threshold? What does that mean to you here? Does it mean anything to you?
The detection level would be the least amount possible for the machine.
Yes, the least amount or concentration. We often work with concentration. The least amount of concentration that can be detected with some confidence. Okay. So different analytical methods have different limits of detection. Some have lower thresholds than others, and that would be beneficial when you're working with components that are present at very, very small concentration. For example, this is kind of a debate, not debate, fun argument I have with Gary. What is better, GC or HPLC? I like HPLC, Gary likes GC. So, but I have to admit that GC has a lower threshold than HPLC, and it's really good for detection, identification, and quantification of components that are present at very low concentration. All right. Now, in terms of sensitivity, what does that word means to you? A lot of people confuse that with threshold. This is related, but not completely. So if you look at A, B, and C, which one you want to guess? Which one?
C.
C, yes, yeah. So the first one is more specificity, A. For B, it is low threshold, that's for detection limit. But C, detection of a minor change in constituent. Let's say I'm doing glucose analysis, and one sample has, just let me write it down. I'm doing the assay, I'm using a spectrophotometer, and then one sample has 10.5, let's say, percent glucose, and then another sample has 10.8% glucose. Depending on the assay I'm using and the spectrophotometer I'm using, the analysis might detect this difference, a small difference of 0.3. And sometimes you cannot detect that small change. So if you have samples that are very close in concentration and that concentration is very critical, like you're preparing media and you really want to be very critical in the amount of glucose you have in there or anything like that, you want to make sure you're using a more sensitive method to detect a small difference between samples, if that small difference is of significance to you. Okay. You will be plotting a lot of standard curves. So we are going to be determining a lot of different concentrations. The first standard curve that you will be plotting, I believe it is the caffeine standard curve in the HPLC lab. So usually standard curves are determined when you have a standard or standard at different concentrations, and then you have your sample, which is the unknown. So you would run your standards, and you take the unit, the observation. Often it's an absorbance, for example, or area under the curve of a chromatographic peak. So you would plot the dependent, which is the observation, absorption, area under the peak, and then the x-axis would be the different concentrations of the standard. Then you plot you do a linear regression, you plot your curve, you get your equation of the line, and you use that to solve for x, which is the unknown concentration in your sample. Y will be the observation, and x is what you will be solving for. So in food analysis, a lot of labs, we're going to plot standard curves. In HPLC lab, in atomic absorption lab, in total carbohydrate lab, a lot of different labs. So we will help you with, guide you with the HPLC lab, and then you will become a pro. All right, so when we select a method, we want to make sure that we have a linear regression that makes sense. So the concentration of the substance is directly proportional to the observation. So absorbance is directly proportional to concentration. We're going to learn about Beer's law later on in spectroscopy section. So we tend to look for linear regression. That would be the easiest for determining unknown concentrations. So we look at observations that are directly related or proportional to the concentration. So linear regression is what we do. So we always have the independent variable, which is the x-axis, concentration of the unknown. Oh, sorry, concentration of your standards. And then we have the y-axis, the observation, which is the dependent variable. R represent correlation coefficient, which is how well the data forms a straight line. So your observation forms a straight line, whether increasing or decreasing with the concentration. And then you have the coefficient of determination, R squared. The higher the R squared, the better is the prediction of your equation of the line. So we always try to get 0.999 if we're able, or something close to that. So this is an example of a standard where BSA stands for bovine serum albumin. You will be plotting something similar in the lab when we learn a Bradford assay for protein determination. So it's a protein standard that we obtain, and we measure the absorbance at under particular conditions, and then we can get the equation of the line and determine the X in your unknown sample, which is the concentration. We'll be doing that a lot. Now, I'll spend a little bit of time reminding you of significant figures. It's very important in this class because you're going to put data most of the time in tables. And you really don't want to put all the big number that you get when you do all a series of addition, subtraction, multiplication, division, and then you get 10 decimal points. You don't want to put that in your table. We need to figure out how to report the data with the significant figures. All right, so again, just reminding you, you all know this, but this just a refresher so that we're all on the same page. I have a few examples. All right. How many significant figures do I have? Huh? 4. Thank you. What about 1? Number 1. 1. Now, it's 3. Okay. So if I have 0.01, is it 3 also? No, it's just one. So it doesn't count. But if you have 1.01, now this zero counts. These zeros count. Okay. Let's say you have a value, let's say 700.0. So all of this is significant figures. So you have 4 here, but a lot of zeros. Can you report that as, let's see. Can you report it like that? How many significant figures? 2. How many do you have here? 4. No, so you cannot. So you have to put, if you really want to put it to the power of something, you have to maintain the number of significant figures. 1, 2, 3, 4. 1, 2, 3, 4. Okay. All right. Let's see, you're doing mathematical calculations, different equations, and sometimes you need to add, sometimes you need to multiply, sometimes you divide. So how do we approach significant figures? So let's say you are multiplying 3 numbers, 36.54 times 238, that's it, times 1.1. So the number is going to be 95. Your calculator is going to give you this number. How would you report it? Yes.
9.6. Fractions, never mind.
You were on the right. What, 9?
10 to the
You,
1, 3.
these are not significant figures. Zeros at the end are not significant figures. So you have 2 significant figures here. The answer will be with the least significant figures. So 96, so you just round it.
Yeah.
You rounded this to 6 and you report these as zeros. Zeros to the right without a decimal are not significant.
But if it was like 9.600, it would have 4 significant figures.
9 point, oh, you can report it as 9.6 like that times 10 to the 3.
Oh, yeah.
You can, for sure. Yeah, good. All right. So what, and let's do an addition and then I'll tell you why it's all up. And usually multiplication and division will have the same rule. You go with the least number of significant figures in your equation. If you have an addition and you have a decimal points, say 7.45 plus 8.725, you get 16.175. How would you report that? When we have decimal points, we go with the lower decimal point. So 16.8. So now why is this important, the decimal point and in analysis? Because you're going to use balances. And you're going to use pipettes, volumetric pipettes, volumetric flask, dilute. You're going to use different tools and they have different accuracy. So let's say you're using an analytical balance and you need to weigh 1 gram of sample let's say 2 grams of sample for ash analysis. So we tell you it should be close to 2 grams. You don't have to exactly get the balance to 2 grams. And then you weighed and you got 1.9981 grams. Your balance read to the 4th decimal. Are you certain to this point? Is the balance accurate to the last digit? Or is the balance accurate to this digit? What do you think? If you don't have anything after this, this is rounded. If the balance reads 6 digits, it might be 0.99808. It rounded it for you to 1 because that's all what it can read. So this is not, the balance is accurate to the 3rd digit. So it's accurate to the 3rd digit, which means your significant figures are these guys. When you want to report, you want to consider 4 significant figures, not 5. When you are using it in an equation, in a multiplication or division or addition, because this is rounded, this is certain. Okay. That's why we want to know a little bit about significant figures, because it impacts your calculations in the lab and how to determine the number of significant figures. Okay, I'm going to give you an example, another example, which will be very relevant for caffeine analysis. You are determining caffeine in, I don't know what samples, some sample. And you had to dilute your sample 50 times, because when you're looking for a concentration in your unknown, you want to make sure that the concentration, when you're measuring, fits your standard curve. It cannot be too concentrated. Your concentration should be within the standard curve. That means within the boundaries of your standard curve. So if you have here 5 ppm parts per million, HPLC is also very has very low detection limit, let's say 5 ppm, 10, 20, I don't remember exactly what the concentration we will be using. So, and you have your standard curve, you have the area under the curve. So your unknown should be somewhere here, should fit like maybe 30 or, oh, sorry, 15 or 30 parts per million. So it should fit the standard curve. It cannot be here because we don't know if it continues to be linear or not. So we have to dilute so it fits within your standard curve. So oftentimes you need to dilute 2 times, 5 times, 50, 100, depends on the concentration of your method that can be used for your method. Okay, so let's say after diluting 50 times, so you took a sample, let's say 1 milliliter, and you put it in a volumetric flask and added water up to be 50 milliliter volumetric flask. Then you dilute it 50 times. And then you got a concentration in ppm or micrograms per milliliter. You got a concentration of 43.5 micrograms per milliliter of caffeine in your sample. So you want to calculate how much caffeine was in the original sample. This is after dilution. So what do? You dilute it 50 times. So what do? It's a sample that is diluted 50 times. If I want to determine how much I have in the original sample, do I multiply by 50 or divide by 50? Multiply by 50. All right, so now you're doing a multiplication. So I have here 3 sig figures. I have 1 significant figure. 5. 1. So now the calculation will be 2175 micrograms per milliliter. How would I report that? If you want to round so that you only have one significant figure, so what would you report it at?
2000.
2000. You would just report it at 2000. What happened now? You killed the sensitivity of your method. You can no longer determine, differences in samples that are close in concentration. So we have an issue. Then I go back and say, is it really 50? Or what is the accuracy of my volumetric flask? The accuracy of my volumetric flask, it measures up to 0.05 accuracy. So, and this is rounded or not, no, accurate to this, all right? So this here, whatever here is rounded, 0, 1, 2, whatever. So it's accurate to this. So if it's 50, then it could be 50.00. Now I enhanced the accuracy of my math. All right, so now I will report it as such, the sensitivity of my math. And if it, let's say if my whatever volumetric flask is accurate to the first digit, then I will report this as 2180. So we always check to what digit is the tool we're using accurate. Okay, so that will help with figuring out the exceptions of the rule when you don't want to really lose sensitivity, and also you want to consider the tool you're using and to what degree it is accurate, to what decimal point it is accurate. Now, there is a common, we'll talk about it in lab when you're averaging. So you're adding numbers and you're dividing. Let's say you're doing 3 reps, and then you are dividing by 3. The 3 doesn't count towards your significant figure. What you're adding at the top counts. This kind of like some exceptions of the rule, but we will talk to you about it when needed during the lab. Okay, any questions? All right. So you can read more about significant figures on page 47 in the textbook. The last bit is important here when you're running a set of replication and you have an outlier. And it's really ruining your accuracy, it's ruining your precision. Then there is a test that you can do. And this comes in handy. Again, another example is the HPLC lab. One group will be doing 2 replication, another group will be doing another 2 replication. We're going to combine the data and you're going to analyze 4 replication. So in this case, that you might have an outlier if somebody else was preparing the rep. So in this case, there is a Q test that you can do, which you take the difference between the 2 adjacent x1 and x2, the 2 nearest to each other, and then the range of your data, the minimum and the maximum. So the one that is in question, you get the difference between it and the next number, next replication. Let's say the replication is 10, and your outlier is 5, and there's another replication that is 9. 5, 10, 9, you're doubting the 5, you'll go 10 minus 5, and then the range of your data. Well, that's a very simplistic example, but you get that. And if your calculated is greater than the tabulated, so we have a table for Q, then you can reject that data point. Okay. That's it. This is what we're doing next week in lab. you will have the information about the lab where you usually find it on Canvas. But what we're going to do is just measuring some water using different tools and doing a lot of calculations and filling an Excel sheet that I will send you today before I leave. We are going to meet in ABMS 135, the teaching lab. We will have a lab coat for you. And then please bring your lab manual or the chapter related to this, which is chapter 6 in your lab manual. And you need your laptop. We will have, I think, 2 extra teaching laptops if you don't have a reliable laptop, because you will be entering data in your own laptop and doing calculations. We'll walk you through calculations together. Okay? So that's that. We can get started with the next, we won't finish it, but we'll get started. All right, so while this might be dry material, it's very important. Sampling and sample preparation is the key for any analysis that you do. If you mess up that part, no matter how good you are in your analytical technique, the results are unreliable. So it's very important, yet it's dry material to know, but some of it is intuitive. Okay. Let's have a look. To determine food quality and acceptance, it is essential to what sounds more logical to you? Emma? C, you said? C is definitely correct. And B. Yeah. The A, you cannot really determine the characteristic of the entire lot until you have unless you have a continuous method that is non-destructive. Like your samples are all going through metal detection, for example. So like your grains are all going through the metal detection and it's not destructive and the whole lot can go through. But when you have tons and tons of material and you just want to look at a compositional analysis, you usually do not measure all your material. You take samples, representative samples of the whole lot to do measurements on. So sample size in this case determines sample size. That means how many samples, not the actual weight of the sample. It is, okay, I'm going to pick out 10 samples or 12 samples or 6 samples. That is the sample size, N equal. So the number of samples that you would pick from the entire lot and how you would pick it. We'll talk a little bit about statistical selections, randomized selection of samples when you have a lot of different or large amount or a lot of different number of samples. So, for example, a plant produces 2,000 cans of soup. So you're not going to measure all the 2,000 cans of soup to determine the nutrition label facts. You would take random samples and do composition notes. How about this one? For sample preparation prior to analysis, the following is true. For all types of analysis, for example, you're determining moisture content, you're extracting fat to determine fat content, you always you mill the samples to a 20 mesh. Do you know what the mesh size is? one mesh is equal to? Have you heard of that before? No, that's fine. It is the number of opening in a sieve in 1 linear inch. When you're sieving your particles, you use different sieves, or even when you're milling, when you want to clarify your fine particles, you use sieves, and there are different sizes, mesh sizes of these sieves, and there are number of opening per 1 linear, not squared, inch squared, linear inch. And the higher the number, the smaller your particles will be, because you will have more pores, smaller pores in 1 linear inch. Okay, enzyme activity should be eliminated or controlled. Lipid oxidation should be prevented. What sounds most reasonable to you? Yes, Al. That's a very reasonable assumption. And in some cases, it's true, all of the above. In some other cases, you need a smaller particle size, higher mesh number. For example, if you're extracting fat to determine fat content, you need at least 40 mesh size. But for other composition analysis, 20 mesh size is fine. But definitely you don't want enzymatic activity. You don't want to store, you took a sample and you're not going to do any analysis until next week. Obviously, you don't want to open the can. You don't want to leave it sitting outside. You don't want the temperature and moisture to be high for enzymatic activity. Lipid oxidation, you don't want oxygen, sample be exposed to oxygen or light or heat. So it will change the characteristic of your sample. You do not want to change characteristic of your sample until you do all the measurements. So it's very important to eliminate any changes in the sample as you select the sample and as you prepare it for analysis. Okay. So is it feasible to evaluate all food or ingredient from a particular lot? We said no, unless it's a rapid analysis. They're all going, the sample, let's say if you are metal detection or doing NIR, IR, samples going through and there's no destruction, and you can get qualitative data, color data, stuff like that. But in most cases, you really have to take a sample. You have a lot of, the lot is huge, and you really have to take a sample and analyze. And samples need to be representative of the entire population. That's why sampling is very important. So the way we sample, it has to be randomized. You don't have to be biased when you're sampling. Therefore, there are certain ways of selecting samples for analysis to eliminate bias so that your samples are representative of the entire population. Sometimes you cannot do statistics. You rely on experience. So this is a truckload of grain, and then you have this experienced guy coming in, picking up samples from that load of the truck. So you would go, well, there's no other way to do that. There's no statistical way of getting a sample of such a load. So when your sample is representative of the entire lot, you can do an accurate assessment and reach a sound decision. Of course, there are sometimes errors that happen and you don't always get to the correct decision, but sampling helps you towards getting to the correct decision and reduce variance. So if your samples are randomly selected, you try to reduce the coefficient of variation among your samples, and then have better precision, better accuracy. So there is something called sampling plan, and sampling plan is, especially if you work in an industry and you are doing the quality assessment, so you really have to have a sampling plan, and that includes many things. So under sampling plan, you have to determine how many samples I should get out of this lot. It's number one, determine your N. Then you have to determine how am I going to sample? Is it a liquid sample? What am I going to use? Is it a solid sample? How am I going to take out the sample? Is it as simple as cans and I just take certain cans from the lot? Sometimes it's harder than that. And then how am I going to prepare my sample? Do I need to homogenize or is it already a homogeneous sample? So sample preparation. And also in the sampling plan, how am I going to store the sample until analysis? Because sometimes you cannot do all the analysis in one day when you sample. So sample storage, or after you take a sample, you have to transport it to the lab. So there is also transportation plan. Does the sample have to be cooled or transported on ice or how? So all of this is under sampling plan. So it's a whole plan, basically. In the past, when students were doing the project, the first component of that project is sampling plan. So they have to devise a sampling plan for ingredients, for during processing, and on the end. So you have to define sampling plan. That's why I put the define, make sure that you remember what is a sampling plan. So, and then also in the last few minutes, you choose your sampling plan based on many factors. So there is table 5.1 in the book that will describe those factors that you would choose. Of course, these are FYI. If you are doing a project, that would be a good table to go to select your plan. But usually you have to say, okay, why am I testing? What's the purpose of the analysis? Is it to accept or to reject a lot? Or is it simply I need to do proximate analysis and I need to do nutrition label? So you really have to figure out why the inspection is happening, and then it would be part of the choice of your sampling plan. Is my product homogeneous? Is my product heterogeneous? Is my product made up of individual subunits? So that will also take part in determining, do you want to use statistics or not in choosing your samples and how many samples. And the list goes on in terms of the factors you need to consider. And I guess I'm going to end it here for you, and then we'll pick up on Monday. So you can start your weekend. Emma, do you have classes after this? There you go. So I was literally between you and your weekend. All right, you guys have a great weekend, and I'll see you on Monday.
Yeah.